talking about higher dimensional isoperimetric and divergence functions for mapping class groups.
Great, thank you. So thanks for the invitation to be here. So it's great to be at the Georgia Topology Conference. I also have a short version of my title. It's just filling functions, which maybe is not as contagious as the last one, although it may still be something you don't want to do at the doctor's office. Raise the -4 so no one gets distracted. So, so the point is that both isoperimetric functions and divergence functions are types of ways to fill things. So what I want to do is start with the kind of the classical version of the isoperimetric inequality, and then sort of remind you about that and how that comes into play in geometric group theory, and then remind you about divergence functions. Meanwhile, I'll sort of talk about how the mapping class groups play in both of those, and then I'll talk about the generalization and the relevant results for the mapping class group. And I should say most of this talk is joint with Cornelia Drutu. Okay. So, so let's start with the classical version of the isoperimetric function. And let me say it for groups. So let's just take a simple concrete example. We'll take z squared, and let's fix the presentation. So AB with the obvious relator, it would be A inverse, B inverse. Okay, so what does the isoperimetric function do? Well, you want to measure elements. You want to measure sort of words that you could write down in terms of A and B, which are trivial in the group, and then you want to sort of measure how difficult it is to make them trivial. Okay, so here's just to draw an example. Here's our Cayley graph with respect to this generating set, and then you just write down some trivial words. So maybe let's write some word which represents a trivial element. So maybe A cubed, B, A, B, and then maybe let's try and make this trivial. So A minus 2, B minus 1, A minus 2, B minus 1. Okay, so everyone can look at that, and you sort of, we know that since we're in a abelian group, we can kind of permute, the A's and B's, and that this represents the trivial word. And if we draw it geometrically, we see that we go across A cubed, and then we go up B, and then across A, and then up B, and then back in A squared, down along B inverse, and then back along A squared, and then down B. So we get this path, we get this image of a circle inside our Cayley graph. And another way to think about the fact that it's the trivial word is that we get a closed loop. So now we have this closed loop in our Cayley graph, and we can ask, can we fill that? So we've got this, I've drawn this Cayley graph in this nice way, so we've got, it looks like a copy of R squared, and we can just ask what's the area spanned by that cycle. So we can just start counting disks, and we see that there's 3, 4, 5 disks here. Okay, so to fill that path of length, whatever it is, it's length 10, took this disk of length 4. Okay, so that's sort of the geometric way you can think about filling this disk. And the algebraic way is, well, one way to think about it is in terms of sort of flipping pairs of elements. Another way to think about that is that since, let's give us a name, gamma. So that's actually the word gamma, and the element of the group is the the equivalence class of gamma. And so so given any word in the generators, in the fixed generating set, the generators representing the trivial word, well, so if it represents the trivial word, we can write it as a product of conjugates of the relator. Okay, and so the one-dimensional filling function, so the one-dimensional isoperimetric function, which I'll write iso sub 1 of my group G, or Z squared here. In this case, it's not just the group, but it's actually the generators and presentation is equal to, well, it's something. It turns out that it's going to be, it's quadratic, but what is it exactly? It's the length of the, so it's the sup over n of the, so you look at all words of length n representing the trivial word. And then you look at the length of those words, so I should say the length of the word. So you look at these, you look at the length of these words, the length of, sorry, the shortest number of conjugates of relators, relators are the inverses of relators, needed to represent this word. Okay, and then you look at the worst of those. So you look at the sup over all words of length n of these ways of representing sort of the trivial word as a product of conjugates of relators. And so, here's one. So here's this word which represents the trivial word. You can write it as a product of conjugate of relators. You'll notice that each one of these blue boxes is corresponds to a relator, but corresponds to a conjugate of relator, because you go over, for instance, A, and then you write the relator, and then you go back along A inverse. So each one of those blue boxes geometrically corresponds to a conjugate of relator, and representing this, filling in this cycle, corresponds to writing that word in such a way, and then counting how many of these conjugates of relators you needed. So, so that's, for a given word, that's the, you can associate this length, and then you look at all ways to represent all ways of length n to represent the trivial word, and you kind of look at the worst way to do that, and that's the one-dimensional isoperimetric function. So this is a map from the positive integers to the positive integers. Okay, so that's the one-dimensional isoperimetric function. So how does this, well, so as I've stated it, it depends on the presentation, but there's a theorem of Behrstock and Alonso, which has, maybe I'll give two formulations of it. So one is that the isoperimetric function of a group, so when we say the growth rate of the function iso1 of group for a finitely presented group is well defined.
So what's the
okay? So let me tell you exactly what I mean by the growth rate. So define, if you have two functions from the positive reals to the positive reals, we say that f is asymptotically bounded by g if there exists a positive constant a greater than 0, such that for all t, for all positive reals, f of t is less than or equal to a times g of a times t, and then you've got it. So it's up to affine functions where you sort of put an affine function every place possible. So let me just write them all to be careful. So up to, precomposing by an affine function and sort of adding an affine function and multiplying by a constant. So f is sort of asymptotically less than g if this is the case, and f is asymptotically equal to g if and only if f is asymptotically less than g and g is asymptotically less than f. So you can think of it as like measuring, for instance, if you have a if f is a polynomial, it measures like the rate of polynomial growth. So the first way it was written down was for polynomial growth functions, this is what you get. But in fact, there's this more general condition. And when you write it down in this more general way, the theorem also due to Behrstock and Alonso, which I think Alonso is the one that wrote down this more general version, is that if groups G1 and G2 are quasi-asymmetric, so any finitely generated group you can put a word metric on. So I'm thinking about G1 and G2 with any word metric, or you can think of G1 and G2 being the same group with two different word metrics. Anytime you have two quasi-symmetric finitely generated groups, then the first isoperimetric function of one is asymptotically equal to the first isoperimetric function of the other one. Okay, so the point is that this is kind of a well-defined invariant that you can associate to a finitely generated group. So it only depends on the group, it doesn't depend on the presentation.
What's the domain of these functions?
Well, they're both from positive reals to positive reals. Well, actually, as I said it, well, in the case that I care about, they're from positive natural numbers to positive natural numbers.
N is the input, right?
Right, n's the input.
The length of words is the input.
The length of the words.
That's what I'm trying to get.
Okay. Okay, so this is the sort of Alonso question, or the theorem. And so now that you know that sort of the isoperimetric function can be naturally attached to the group without depending on the generating set or the choice of presentation, you might want to ask sort of what else it sees. So, so a theorem of Gromov's is that, well, what's the simplest first isoperimetric function that can occur? Well, it could be linear. And it turns out that if it's linear, that's equivalent to being G. That's equivalent to G being subquadratic, so little o of x squared, so less than any quadratic function. And that occurs if and only if G is delta hyperbolic. Okay, so the first isoperimetric function, it can be linear if and only if your group is a delta hyperbolic group. So this is sort of one way that you can sort of see certain classes of groups from this function. Another way this is shown up is a theorem of, I should say, Epstein-Thurston. So they proved that if a group G is automatic, or actually more generally they showed that if the group has a quasi-geodesic homing, then the first isoperimetric function of G is at most quadratic. It might be linear, it might be quadratic, but it's at worst quadratic. This doesn't characterize all quadratic functions. There's quadratic functions which aren't automatic, which aren't even combable. But it's a way of sort of picking out some class and showing that their isoperimetric functions behave in a nice way. So this is a result of Epstein-Thurston, which will relate to some stuff which will relate to the mapping class group. In fact, it relates to the following theorem. So Leuzinger has this important annals paper where he proves that the mapping class groups are automatic. And so the automaticity via the Epstein-Thurston theorem then tells you that for a mapping class group, so the first isoperimetric function of the mapping class group of a surface is always, is at most quadratic. And in fact, they're almost always quadratic because there's only a few mapping class groups that are hyperbolic. So they tend to be quadratic, except for in the few low complexity cases where they're finite or where they're hyperbolic, and they're hyperbolic in either of those cases. In those cases, it's linear. Okay, so that's my sort of quick summary of the classical isoperimetric function. So let me now say a little bit about the divergence function. So the isoperimetric function, the one-dimensional isoperimetric function, was about taking these one-dimensional spheres and then filling them with disk. So the divergence function, so really the classical version is the zero-dimensional divergence function. So the divergence function looks at filling, instead of filling circles by disk, we start with filling pairs of points by lines, okay, by line segments. So you fill a zero sphere by a one-dimensional ball. And the reason that can still be interesting is that well, I want to fill, but if I just filled by a geodesic, since the Cayley graph is a geodesic metric space, that would just tell me the length of the distance between those zero spheres. So just filling in any edge wouldn't be interesting. Filling in any one-dimensional ball wouldn't be interesting. So you want to add some constraints. So the constraint that you add is you say, I'm not going to fill in just any one-dimensional ball. I'm going to require that it avoid, so I'm going to think of these two pair of points as A and B. I'm going to look at any other point C, and I'm going to avoid a large ball around C. Okay? And then I'm going to ask, what's the shortest path between A and B? So I want to measure, so the divergence function is going to consider lengths of paths which avoid large balls around a third point.
Minimum or few?
Well, it's going to be both,
Okay.
around a third point. Okay, so why do I say both? So what do you do? So for a given pair of points, so for a given triple of points A, B, and C, what do you do? So for given points A, B, and C, you look at so there's actually a constant that I need to fix once and for all, which turns out things aren't going to depend on, but you need to fix one. So you fix some constant delta between 0 and 1, and then you take your pair of points which don't all coincide, they're all distinct points A, B, and C, and then you remove this ball, and the ball you move is going to have radius. So this radius is going to be delta times the distance between the distance between C and the set A, comma B. Okay, so sort of a model to think about is A and B lie on some geodesic, and often the worst case is that C is in the middle of that geodesic, and then you remove a ball which is linear in the distance between A and B. Okay, so I remove that ball, and then I want to find the shortest path. So this will be the shortest path. Shortest path in my space minus this red ball. Okay, that's the divergence associated to a triple of points. And then what I want to do is I want to look at all possible configurations of triples of points where A and B are distance n, and I want to look at the worst possible way to do that. Okay, so that's the divergence, and then that's going to be a function of n. So for any n, I'll look at all possible triples of points where A and B are distance n apart. Okay, so this distance will be some fixed number n. Look at all pairs of points A and B distance n apart, and all points C anywhere in the space which are distinct from those, and then look at the length of the shortest path for any one of those triples, and then this gives me a function again. So the zero-dimensional divergence will be a map from again the positive naturals to the positive naturals, which tells you how long those paths are that avoid these balls. And again, actually, the path may not be defined if you have a space that's not one-ended. Then things won't be defined. So we generally assume that we're in a one-ended space to make the parallax simple. So so really here this is union infinity, and what we really care about is the one-ended case. Okay, so that's the zero-dimensional divergence function. So where does that come in? So again, we can start with a theorem of Gromov's. So again, maybe henceforth I'll assume that my spaces are one-ended. Okay. So but maybe here in purposes I'll say it one more time. So if you have a one-ended hyperbolic group, then its zero-dimensional divergence function, its div sub 0, is exponential. Okay, actually, maybe before that I should have had a pre-theorem, but anyways, I guess in the order that these things were defined, that was maybe the first theorem. And then, maybe to make sure that I've hit all the necessary prerequisites, let me just say a theorem of Drutu, Moses, and Sapir. So they proved, so just like for the one-dimensional isoperimetric function, you want to know that it's well-defined and associated to your group and it doesn't depend on a generating set. So they proved that the the asymptotic class, so the asymptotic class of div 0 for a finitely generated group doesn't depend, well, is well defined and is a QI invariant, is a quasi-symmetry invariant. Okay, so two things. One was I fixed some delta to start. It turns out that if you take a different delta, you'll get another function, but those two functions will be asymptotically equivalent. So they'll agree in this way. And if you took two groups that were quasi-symmetric to each other, or the same group with two different word metrics, so that you have the same group and it's quasi-symmetric to itself, then you'll get two different divergence functions, but they'll also agree up to this equivalence. So as long as I only ask questions about this equivalence, I get a well-defined invariant with the group. Okay, so and that equivalence, anytime you're in the situation where you have a one-ended delta hyperbolic group, so I said hyperbolic group is actually a delta hyperbolic group, this works for, then you get an exponential divergence function. And you can see this, right? This is a fact that everyone knows, because for instance, in classical hyperbolic space, if you just look at the perimeter around the ball, that perimeter is, well, everyone knows except for me, it's either hyperbolic sine or hyperbolic cosine. So, right? Yeah, my hyperbolic trig is always off. But anyways, it's one of those functions. Those are both exponential functions, so it doesn't even matter which one it is. And so you get an exponential function associated to the divergence for that's if you're in actually a hyperbolic group, and if you're in a delta hyperbolic group, then you can get the same sort of argument to work. There's ways with projections, and there's a couple different methods to show that. So a delta hyperbolic group gives you exponential divergence function. On the other hand, if you have the group that I started with, z squared, well, that's got a linear divergence function, because the isoperimetric function in Euclidean space. If you have a ball, a 5-year-old knows that if you have a ball and you look at if you have a disk and you look at its boundary, then it's the circumference of that, well, half the circumference is pi r. So there's your linear function, and so that gives you the linear divergence for your it gives you the linear divergence for z squared. Okay, so sort of linear divergence occurs in Euclidean cases, and exponential occurs in hyperbolic cases. So let me then state a mapping class groups theorem. So actually an older theorem of mine, that the mapping class group of a surface, well, outside of the hyperbolic cases, so as long as with the complexity of S greater than or equal to 2, right? So the complexity of S, I think, for me is always 3G plus P minus 3. So as long as you're not a hyperbolic group, then mapping class group with this has zero-dimensional divergence, which is quadratic. So let me just remind everyone why that's the case. So I mean, it's a little surprising. You might think that it would be exponential, but it's not. So here's maybe a sketch of the proof. So why is it? Maybe first I should say, why is it superlinear? So why does it grow fast? So let's do the why is it? So zero-dimensional divergence bigger than or equal to x squared. So how do you show this? Well, you take the paths that you think should behave like a hyperbolic path, right? So you take the axis of a pseudo-Nassau. So let this be, so inside the Cayley graph, you think of the orbit of the pseudo-Nassau. And then you prove the following theorem. You prove that if you're disjoint from the pseudo-Nassau, if you take some point, which is not in the pseudo-Nassau, and you take the ball around it, so that the radius of that ball is less than the distance to that pseudo-Nassau, then I prove that this has a sort of contraction property. So if you take linear-sized balls that are in the complement of that axis, and you look at the closest point, so for any one of those points, you look at the closest point on the axis to them, then it turns out that the set of all those closest points has a uniformly bounded projection. So in other words, that there exists constants, I'll call them maybe delta and v for bound, such that for each x in the mapping class group minus this axis, maybe I'll call this gamma, minus gamma. So anytime you're off gamma, then the closest points, so the closest points on gamma to the ball of radius delta times the distance between x and gamma. This has this is uniformly bounded by v. So I'm using v in no ways here, but so this is a ball. If I take the ball of some linear distance, some linear size. So for any point, there's a linear sized ball, and those linear sized balls project to uniformly bounded diameter sets when you look in gamma. And so what does that mean? So that means that if I wanted to avoid a large, if I go back to kind of trying to avoid one of these large balls there, I try and avoid a large ball on the pseudo-normative axis, well, once I'm out here, in order to go some uniformly bounded distance inside here, I've got to move a linear distance out here. So my blue path, to get very far, I've got to move these to go this uniformly bounded distance here, I've got to move some big distance, and then over here, I've got another ball to move the same distance here. And so to go a linear distance along the pseudo-normative, I've got to go through a bunch of these very long paths over here. And so I've got at least, so this is uniformly bounded, so if the length of gamma, if I look at a length n segment of gamma, then I've got to go through n of these, and I've got to go through each one of these n things for a distance approximately n. So it's linear times linear, so it's at least quadratic. So the length of this is at least quadratic. And well, the upper bound is maybe not so much relevant for the rest of my talk, but I can't resist giving a short sketch of it. So, so the fact that the bound is less than or equal to x squared is just the following thing. It's like 3 sentences. So you're in the mapping class group. So you look at any infinite path in the mapping class group. So for instance, look at your pseudo-normative, and then factor that as a word in some generating set. And what generating set do I want to take? Well, let me take the set of Humphrey's generators. So the point is, there's some collection of Dane twists that has the following nice property. So you don't even have to know what they are, but something like this. So you've got this collection of curves, and Dane twists along those curves generate the mapping class group. So given any path, I can think of factoring that as a word in terms of these generators. Okay, so I factor my path. Now, what nice property does this collection of generators have? It has the nice property that any two of these curves are either disjoint, in which case, since they're disjoint, they span a free abelian subgroup, and in fact, those free abelian subgroups are quasi-symmetrically embedded. Okay, so either they're disjoint and they span and they sort of sit inside something that looks like Euclidean space inside your group, or they intersect. But the ones that intersect, those pairs are both simultaneously disjoint from something else. And so even though they intersect, they're both disjoint from something else. So then there's a pair of flats which each intersect, which each sort of share a common curve, which both share a common curve. And so you've got a pair of flats that intersect along the line. Okay, so now you take this. So here's my geodesic, and I've got this ball I'm trying to avoid, and I want to get from this point to this point. Well, I've now factored in terms of these Dane twists, and any pair of these either lie on a flat, or if I add one more vertex out here, there's a flat here and a flat here which intersects. So there's a sequence of these quasi-symmetrically embedded flats, and the length of those is at most twice the length of my original path. And each one of these flats has linear divergence. And so then I kind of use the fact that these flats, in Euclidean space I have linear divergence, and I only have linearly many of them, and I start avoiding things in those, and I show that the upper bound is linear times linear. Okay. So that's kind of the quick sketch of how you show that it's exactly quadratic. And I'll come back and sort of mention this again later. Okay, so that's the sort of classical divergence functions. All right, so now let me set up. Actually, there's no clock in this room. Okay. Good, I've got a clock now. So that's the classical divergence function. So let me now say what the higher dimensional divergence, what the higher dimensional filling functions are. Okay, so this is the context that I work in. So there's a bunch of different contexts where you can talk about spheres and filling spheres, right? You can talk about, there's integral currents, and there's, Lipschitz maps, and there's homology spheres, and so there's a bunch of ways of doing it. So the way that and they turn out to all be sort of, equivalent in the places where they coincide. And so the way that Cornelia Drutu and I sort of approached this was through a more combinatorial approach that allowed us to kind of explicitly count things. And so, so it works more generally than the mapping class group, but I want to get to the mapping class group theorem, so let me just say what the setup is. So the setup works for any group, let me say group G, which is an F, n, what do I want to call it? Fn plus 1. Okay, so that just means that it has a, i.e., there exists a kg1 for the space for the group with a finite n plus 1 skeleton. Okay, and I'll usually, so for the next few minutes, I'll let Y denote the universal cover of this KG1. All right, so that's the context, and then the remark is is that Epstein-Thurston. So they proved that any automatic group, in fact, any combable group, is of type F sub n for all n. Right. So they admit k pi 1s with a finite n skeleton for every n. Okay. In general, I want to work with the n plus 1 skeleton because I want to work with a space which is contractible, dimensions less than n, but has dimension n plus 1. So that's the remark, and so I guess the second part of the remark is, hence, the mapping class group fits in this context. Okay, so the constructions that I'm going to give work for the mapping class group, and in fact, there's been explicit constructions of nice classifying spaces for the mapping class group. There's one by, G and Wolpert, Scott Wolpert wrote down one, and Muslin wrote down one, and so there's sort of explicit constructions of nice k pi 1s to work with for the mapping class group. So we want to fix one of those, and then sort of work with the combinatorial structure that gives us. Okay, so here's the. Actually, let me just say one more thing, which is, so I want to do this with the finite n plus 1 skeleton. I want to think of this as having a fixed simplicial structure. So let denote the universal cover with a fixed, right? It's got this fixed simplicial structure. Okay, so now what I want to do is now I can talk about mapping spheres into that or mapping any spaces into that and thinking about kind of the combinatorics of those spaces. So the next definition is that an m-dimensional domain in Y. Okay, so I fix this space Y, and an m-dimensional domain in Y is a pair. So is a simplicial m-dimensional manifold.
This Y is just some space, or it's?
It's one of these spaces.
Cover
It's a group with finite, it's a group that has a k pi 1 with a finite n plus 1 skeleton. Okay, so an m-dimensional domain in Y is some arbitrary simplicial m-dimensional manifold, and a singular simplicial map into Y. Okay, so it has its own simplicial structure, and then it's being sort of mapped into the space Y. And so one thing is, for instance, it may collapse everything to a point. So even though I'm calling it m-dimensional, when it's sitting inside my my space Y, it may actually just be a point. Okay, so but what I care about here is what the what the domain was that it started with in its original structure. So that's what an m-dimensional domain is. And then I can measure the volume of one of these. So the volume of an m-dimensional domain is the cardinality, so it's the number of m-dimensional simplices on which this map in is a homeomorphism, on which the map is a homeomorphism. Okay, so now I've got a way to measure volume up to the dimension of the up to n plus 1.
So if two simplices have the same image, are they each counted in the volume?
Yeah, that's right. So on each, you look at each simplex and you look whether that simplex is being mapped in homomorphically, and if it is, then you count one towards the volume.
So if two have the same image,
then it has, well, that's fine. It may have, it has volume 2. I mean, if there's only 2 where they map in homomorphically, but they map onto themselves, all you care about is the map restricted to that simplex. Okay, so that's how I measure volume. And then I've got to think about fillings, right? So I care about, what I care about is not just the volume of one particular manifold, but what I want to do is take a manifold with boundary and I want to take a pair of things where I've got a map in of some manifold, which is m-1 dimensional, and then I've got another m-dimensional manifold whose boundary abstractly has a simplicial structure that agrees with the m-1 dimensional manifold I've mapped in, and then I want to map in that pair. And then, okay, so that's what it means for one manifold to fill another one. So, so the filling volume of a let me call it H, an m-1 dimensional domain. Actually, let's just say m-1 dimensional domain. That's fine. Which whose underlying space is the m-1 dimensional sphere. You could do this more generally, but for now, the filling volume of an n-dimensional domain whose underlying space is the m-1 dimensional sphere is the infimum over all m-dimensional vols. Mapping into of all domains which are whose underlying space is an n-dimensional vol and whose simplicial structure on its boundary on their boundary agrees with the original sphere you started with, agrees with the sphere. Right, so anyways, because this is maybe much clearer with the picture. I mean, you have this space over here. Here's your space Y, and you've got this map in of a sphere. So when the fact that this is a two-dimensional sphere being mapped in as a domain means I've got some fixed triangulation on that, and I've mapped it in, and then a filling of that corresponds to some ball. So now some solid ball, which then has an induced structure on its boundary, and the induced structure on the boundary is simplistically equivalent to this one, and then this maps in and fills up that space. Okay, so this is what it means for one thing to fill the other, and the filling volume of H filled by this ball is the infimum over all balls which fill that. I should say maybe over the volume of all balls. Over the volume of all balls which fill the sphere. Okay? So I look at, there's lots of different balls that I could now, there's lots of ways that I could map a ball into the space so that its boundary agrees with this boundary. And I look at every possible way of doing that, and I look at the smallest volume of a ball, so the n-dimensional volume of this n-dimensional ball that's mapping in. Okay, so that's what the filling volume is. Okay, so then there's a couple, right? So then there's a couple remarks I should make. How much time do I have? I think I have enough time. So what are the remarks? Well, the first remark, right? So the first remark is that this gives me a function. Okay, so the k-dimensional? Maybe the rest of the definition is that the k-dimensional isoperimetric function of y, right, is this map iso sub k, which maps, well, let's just take it from the natural numbers to the natural numbers union infinity, which sends, x goes to the sup over all h of the filling volume of H. So the fill volume of H, and what's my condition on H? It's the fill volume of H, where H is H is a sphere. H is SK. Right? It's a k-dimensional sphere, and the volume of SK is at most x. Okay, so I look at all spheres that map into my space that have k-dimensional volume x, and then I look at right. So these things all have k-dimensional volume at most x, and then I look at all fillings of balls by that, and I measure the volume of those balls that fill them. Okay, so here's the classical example, which calls the theorem. So Federer and Fleming. So this is sort of a classical theorem in geometric analysis. Is that for k between 0 and n, the n has kth isoperimetric function equal to, or asymptotic class is equal to x to the k plus 1 over k. And this bothered me for a long time. There's a normalization issue here, which is weird. So you think of the k-dimensional sphere, you feel like it should have dimension k. It should have volume x to the k, but I've normalized it, so I'm looking at them with dimension x, and that's why this is x to the k plus 1 over k instead of just x to the k plus 1. But anyway, so this is the classical theorem that for Rn this is the case, and sort of ours, so we've now sort of put this in a combinatorial. We actually give a proof of this, but we put this in sort of a combinatorial framework where you can then think about the isoperimetric function of z to the k also, and you also has has these same functions. So anytime you have an isoperimetric function with this growth rate, so we call this, people call this, it's a sort of standard name, so this is called a Euclidean filling function, a Euclidean isoperimetric function.
What's the kth isoperimetric function?
Okay, well, okay, so right, so I've defined it for the space Y, and then so the point is that the kth isoperimetric function of the group should be the same as the kth isoperimetric function of this associated, universal cover of the k pi 1 for the space. So in order to do that, you need a theorem. So let me just, I'm not going to write it down carefully, but let me just say what the theorem is. So Alonso Pride and Wang showed that, I'll just write it like this. So this is a little sloppy, but iso sub k of a group, maybe of a space Y is up to this equivalence function a quasi-isometry invariant.
I just don't know, what does the K do?
Okay.
I don't know if you, you
so
described ISO sub 1, but I don't know if you described ISO sub 1.
well, so K is the dimension of the sphere.
Okay.
Yeah, so you could put in a k-dimensional sphere and then fill it by a k plus 1 dimensional ball. That's what the k is. You get a different one. So the one-dimensional version, iso sub 1, is you put in a one-dimensional sphere and you fill it with a ball. But you could do that for any dimension.
Okay.
And so these give you functions. And so one needs to be a little more careful when you write it down. But anyways, the point is that if you're in the context that we're in of a group that's it's an fn plus 1, then for any k less than n, the isoperimetric function is well defined as a quasi-isometry invariant to the group. So two different ones give you functions that agree up to this asymptotic equivalence. Okay, so all right, so let me state the theorem then. Let me state one of the theorems. So the first theorem with Drutu is the following. So let S be a compact, well, I'll just say surface, a compact orientable surface of finite type. Okay, and I'm going to use I'll use the complexity. So C of S is 3G plus P minus 3. That's, everyone uses that, so I just wrote that quickly. So you just have some surface and you've got that measure of complexity. So we want to know what the different isoperimetric functions are. So we prove the following. So if K is less than the complexity of the surface, then it has a Euclidean filling function. Then iso sub k of the mapping class group of S is x to the k plus 1 over k. Okay, so all the filling functions less than the complexity are Euclidean filling functions. And if k is bigger than or equal to the complexity, then these kth isoperimetric function, I'll just write iso sub k, then the kth isoperimetric function is little o of, it's sub-Euclidean, it's little o of x to the k plus 1 over k. Okay, so it goes slower than this Euclidean function. And in particular, moreover, if in a few cases, or in some cases, if the genus of the surface is either 0 or 1, or S is equal to the closed genus, the closed surface, maybe I'll just say it, or S equals the closed surface of genus 2, then we can prove that these higher dimensional isoperimetric functions, when k is bigger than the complexity, are not just sub-Euclidean, but they're actually linear functions. Okay. So below the complexity, the functions are Euclidean, and above the complexity, above or equal to the complexity, they're sub-Euclidean, except for, in this case, well, except for these special cases where not only are sub-Euclidean, but they're actually linear. Okay, so this theorem sort of generalized. The only known result of this beforehand was this result I told you at Mosher's, that the first isoperimetric functions were quadratic. So that sort of coincides with this, but we cover the rest of the cases. I guess actually it also follows from his works that they're at most polynomial, but there were no explicit bounds. So we give very explicit bounds.
Hey Jason, you said the little o of x to the k plus 1 over k. Do you know that they're not actually just x?
No, I expected they're x. Yeah, I mean I think conjecturally they're x, but we don't. Yeah, we don't know that. So this is not known to be sharp. Right. Let me put up the other theorem, and then I'll tell you why. Maybe you already know why those cases are special. Okay, so that's one theorem. So the other theorem. Same two of us. So again, it's the same setup. So we want to compute, so these were the isoperimetric functions. We also want to compute the divergence function. So here, we know that if k is less than the complexity, then the kth isoperimetric function is, let's write this. So it's at least, so it's bigger than or equal, remember this means sort of bigger than or equal to, it's at least x to the k plus 2. And, right, I want to say anything there. No, it's at least x to the k plus 2. And if it's bigger than or equal to the complexity, then iso sub k is.
Do you mean divergence?
Oh, sorry, right. I wrote iso. Divergence. Thank you. Right. Otherwise, that would be okay. Right. Then we have to erase the video if that was true. All right. So right. So if you're less than the complexity, then you're at least x to the k plus 2. And again, I don't know that sharp, but in some cases it is. And if you're bigger than or equal to complexity, then you're little o of x to the k plus 1. Right. And again, there's a moreover here. Moreover, if you're in these same cases, if the genus of S is either 0 or 1, or S is closed genus 2, then we get that it's exactly, in fact, x to the k. Then the k-dimensional divergence is x to the k. Okay, and so what cases of this were known? Well, there were two cases that were known of this, actually. It was known, as I told you at the beginning, the zero-dimensional divergence is actually known to be exactly x squared. So this sort of agrees with the zero-dimensional result. And so that was one case that was known. And there was another case, let's see, what are the right names? Abrams, Brady, Donnie, Duchin, and Young. So they proved that the one-dimensional divergence is always, at most, x to the 4th. So our theorem in the one-dimensional case shows you that it's at least x cubed. I mean, I think ours are sharp. So we don't know how to get the upper bounds, but I expect that these bounds are sharp. And they show at least for the one-dimensional case that it's at most it's at most one more than what we put. So maybe in the last 5 minutes. So let me just say what the analogy is. So where did these theorems come from? Well, in some sense, they're generalizations of, it sort of generalizes this theorem, this old theorem of mine about the divergence, the zero-dimensional divergence of the mapping cross group. But another reason that we wanted to think about these was there's been a whole kind of a bunch of results by different people. So Gromov, Brady Farb, Hindawi, Leuzinger, Wenger, Young have all been involved in sort of studying these high-dimensional divergent isoperimetric functions for Hadamard groups and Hadamard spaces. And there they proved a bunch of theorems, and they all have a very similar flavor. In fact, maybe I should just write one of them down. I mean, so in parallel to what we did, we were sort of motivated by their theorem. So the analogy is for Hadamard groups, so fundamental groups of complete cat0 spaces. So for Hadamard groups, so what do they prove? So for instance, let me just write the divergence. They prove that the k-dimensional divergence is bigger than or equal to, or bigger than xk plus 2 if k equals the rank, right, the rank of the Hadamard space, so the maximal dimension of the Euclidean flat, the rank minus 1. So kind of our theorem works everywhere below the rank. They do it in the one dimension right below the rank. They prove this. It sort of, well, it requires like those 6 different authors that I just mentioned, and they show that the k-dimensional divergence is less than x to the k plus 1 if k is bigger than the rank. If k is bigger than the rank. Well, sorry, bigger than or equal to the rank. And then in symmetric spaces, they can actually show sharper balance. They can show, for instance, that this is strictly less than that. And there's a number of, so anyway, so it's the same kind of, it's the same basic framework, but it's kind of, it's interesting. I mean, this is one of these parallels that I've been sort of obsessed with for a while, that there's lots of ways that the mapping class group sort of behaves like a non-positively curved, like a Hadamard group. Even though, there's this theorem of Kapovich and Lieb that it's not a Hadamard group. So it doesn't act nicely on a even without properness, it doesn't act nicely on a cat0 space, on a complete cat0 space, but yet it sort of has all these strong parallels. So let me just, in the last 2 minutes, let me just maybe sketch one of these things. So maybe, let me give an idea maybe of this divergence, because it relates to the lower dimensional divergence, the zero-dimensional divergence I said at the beginning. So I said before that if you had zero-dimensional divergence, it was it's exactly quadratic. So, but if we think about the bound that it gets at least quadratic, so that comes from looking at a pseudo-Nossoff and trying to avoid a pseudo-Nossoff. So one thing that we show in our paper is that there's really natural spheres, kind of higher dimensional spheres that have sort of interesting higher dimensional divergence. So so the picture, right, the picture there was we looked at an axis of a pseudo-Nossoff. So we had the pseudo-Nossoff, and then we wanted to we wanted to avoid this kind of large ball. So there was our zero-dimensional sphere, and then we filled it. So what are the one-dimensional spheres? Well, the idea is that you take your surface and you decompose it into 2 parts. Okay, so for instance, take a separating curve, and you look at these 2 different subsurfaces, and then you take two different maps, 2 different partial pseudo-Nossoffs. So one which is pseudo-Nossoff on this blue side, maybe I'll call that G. So G is pseudo-Nossoff here, it's PA here, and it's the identity over here. And then you take another pseudo-Nossoff, maybe H, where H is pseudo-Nossoff here, and is the identity on this half. Okay? And then you build, so then you sit in a flat. So you sort of build this flat, which look like here's powers of G, here's the axis of that in the mapping class group, and here's the axis of the L, here's the axis of G, and here's the axis of H. Okay, now they span, these 2 things commute. So there's this big Euclidean flat sitting in here. And in that Euclidean flat, you can look at, these big, you can look at big circles in that flat, big squares in that flat. And now the point is, if you want to fill that square, well, you can fill it, right, you're sitting in a flat, so you can fill it, if you just want to put it in a flat, well, you put it in the inside of the square. But now if I wanted to look at divergence, well, I did tell you the high dimensional diversive divergence, but you can imagine what it is. It's the same thing. We look at fillings, and we want to avoid large balls. So now I want to avoid a large ball that's in the middle of this square. And the problem is, when I try to fit something in, well, you can sort of go back to these, eventually it relies on the distance formula, but there's these kind of intricate theorems about how the distance has to work. And so here we know there's a contracting map in the complement of this axis. So here we have this kind of product of 2 naturally there's like a product of this subsurface with this subsurface, and that sits nicely inside the mapping class group, these product of these two subsurface stabilizers. And in fact, inside that, you can prove that if you take the axis of H cross the whole stabilizer of the other subsurface, and the complement of that, there's a contracting map. And in the complement of G cross the whole stabilizer of this other subsurface, there's a contracting map. And then you sort of look at where this square would have to go, and it would have to lie in the intersection of those. So you can show that there's sort of contractions anywhere you leave this square, because either you're going to have to contract in the H direction or contract in the G direction, and in most ways you're going to kind of contract both ways. And so kind of you end up needing to apply sort of two different versions of this same sort of contraction. So instead of getting quadratic, you get another dimension of, you get one more degree of contraction in this case. And then we kind of iterate that up. So we build all these very natural spheres that are hard to fill with balls. And maybe we can just stop there.